Kia ora and welcome to question 5, the last question in the 2008 Skull Calc exam. This question has 3 parts and they are all conics related. As I've mentioned in previous videos, conics was an external assessment in the NCEA back in 2008, so it seems to feature quite heavily in scholarship exams alongside the other 3 main topics: differentiation, integration and complex numbers. So this first part here, finding the Cartesian equation of the curve, you may not have seen parametric equations for conics if you did the conics internal assessment, because current NCEA, the internal assessment is a modelling based assessment where you can just stick with Cartesian equations. Here we want to convert between parametric equations and the Cartesian equation. I can look at this and know that it's going to be a hyperbola, and I'll explain why in a sec. That was not an intentional pun, but I'm pretty stoked I just said that. If we look at the formula sheet for Skull Calc, and so it's handy to have one in front of you for this particular part, under hyperbola, it's got a Cartesian equation, x squared over a squared minus y squared over b squared equals 1. You can swap the x and y around there and get a hyperbola that opens upwards and downwards, as opposed to this one which opens left and right. Okay, so the equation here will look like this. And it's also got the parametric form beside it. It says or a sec theta b tan theta. Now those coordinates there are similar to what we've got. We've got a sec theta and we've got a tan theta. And we could say that in this case a is equal to 1 and b is equal to 2. But the other extra thing is the transformation. The minus 1 is saying take 1 off all the x values, and the plus 2 is saying add 2 to all the y values. So our Cartesian equation for this is going to be x plus 1 all squared over a squared, where a is 1. I'll just put 1 squared so that we can see this, the link, minus y minus 2 all squared divided by b squared, and b is 2, so 2 squared equals 1. Now why did I go plus 1 and minus 2? Well, we know that when you have a plus 1 in there, it moves the graph to the left, to the negative side. And when it moves to the left, you're essentially taking 1 off all of the x values. Likewise, y minus 2, that's a shift upwards by 2, which is the same as saying add 2 to all the y values. So that's the Cartesian equation that the question wanted us to find. How could we find that without a formula, and how did I know that it was a hyperbola equation? Okay, so we can just take the parametric equations and rearrange them. So x plus 1 is equal to sec theta, and y minus 2 is equal to 2 tan theta. Actually, I'm going to divide by 2 as well. So y minus 2 all over 2 is equal to tan theta. Now if I square both of these, and that's the trick here, if I square both of them, I get x plus 1 squared is sec squared, and y minus 2 all squared divided by 4 equals tan squared. And then we relate this to our trigonometry. We should know the trig identities pretty much off by heart if we're doing scholarship, at least the basic ones. So we know that there's a formula that says sec squared minus tan squared equals 1. And if that's true for all values of theta, that means that x plus 1 squared minus y minus 2 squared over 4 will always equal 1. And that's the equation that I found using the formula sheet, but I've just derived it using a trig identity. So there's the Cartesian form, or Cartesian equation, for the hyperbola that we're dealing with. Alrighty, part B. The normal at the point P, where theta equals pi over 4, meets the curve again at the point Q, in the region where x is less than 0. Find the y-coordinate of Q in the form of a over b. Okay, so we've got an equation of a normal, which we need to find, and we're told that theta equals pi over 4. So it helps us to draw this picture first and say, look, let's look at the hyperbola, draw it roughly to scale, then we'll draw this normal in. and go from there. So, okay, this hyperbola, the a value is 1. Okay, what that means is that the vertex occurs 1 away from the centre, but the centre is not at the origin anymore. The centre, which normally would start at the origin, has had a shift to the left by 1 and up by 2. So actually the centre's there, where that's 2 and that one there's -1. And then we draw the hyperbola 1 away from that, something like that and like that. Okay, that distance there from the centre to the vertices of the hyperbola are equal to 1. And then lastly, the b value is 2, and what that means is that the slope of the asymptotes is b over a, or plus or minus b over a, plus or minus 2. So we take some asymptotes centered at the center of the hyperbola and draw them in with a steepness of 2 and -2, or gradient of 2 and -2. So I've kind of roughly done that to scale, but that means my hyperbola needs to be a little bit, well, the shape needs to change a little bit. You can use your graphics calculator. A Casio graphics calculator will do conics, or you can rearrange the Cartesian equation and make y the subject of it. So if you go back to this equation here and you go y equals, you can put it into the graphs menu. You make y the subject, you're going to have two curves, a plus and a minus for the square root, and that will give you the top and the bottom of the hyperbola. Okay, now we're told that theta equals pi over 4, there's going to be a normal. So we first up need to find where is theta equals pi over 4. Let's go back to the original equation and substitute theta equals pi over 4 into this equation. So we've got x equals sec of pi over 4 minus 1. Let's draw a triangle with an angle of pi over 4, 1, 1, root 2. Sec is the reciprocal of cosine. Cosine is 1 over root 2. So sec is root 2 for this angle. And similarly, find the y value, 2 tan theta. So 2 tan of pi over 4 plus 2. Tan pi over 4 is opposite over adjacent. 2 times 1, and then plus 2 is 4. So that's our coordinate where we're drawing the normal. X equals root 2 minus 1, so that's about 0.4, and y is equal to 4, looks like about there. That's our point P, I think. Yep, normal at the point P meets again at the point Q. Alrighty, so if we put P there and we draw in some normal, oops, I missed the spot, go through P, something like that. It's going to meet over here at Q. Alrighty, so how do we find Q? Well, we just need to find the equation of the normal and solve a simultaneous equation. To find the equation of the normal, we need to use differentiation to find the gradient. You can use either of the Cartesian or the parametric forms to do that. I'm going to use the parametric because it's nicely set up and I can substitute pi over 4 into it. Okay, so starting again with our equations, sec theta minus 1 and 2 tan theta plus 2. Differentiation using parametric equations, dy dx is dy d theta divided by dx d theta. Dy d theta, the derivative of that second equation, is 2 sec squared theta. And the derivative of the top equation, the dx d theta, is sec theta tan theta. Okay, the sec theta cancels on top and bottom. So we've got lose that one, lose that one. We end up with 2 sec theta over tan theta. And we want to substitute theta equals pi over 4 in for the specific gradient at P. at point P, theta equals pi over 4, dy dx is equal to 2 sec theta. Remember, I'd already found what sec theta was for that particular angle. It was root 2, and then I took away 1 from it, but sec theta is root 2, and tan of theta was 1. So I've got 2 sec theta, 2 root 2 over 1. Subbing in pi over 4 gives me that, and therefore the normal gradient will be negative 1 over 2 root 2. Bearing in mind that when you find a normal gradient, it's the negative reciprocal of the tangent gradient. Okay, now we go back to the problem. We're trying to find this coordinate q, the y-coordinate of q, and apparently it's a fraction, where a and b are integers. To do that, we're going to solve this equation of our normal simultaneously with the equation of the hyperbola. So the normal is a straight line. Y minus y1 is m times x minus x1. x1, y1 is a specific point on the normal. We're going to use the point P. Remember that P had a coordinate of root 2 minus 1 for the x value and 4 for the y value. So our normal has an equation of y minus 4 equals minus 1 over 2 root 2 x minus root 2 minus 1. Be careful with that, there's brackets inside brackets. Now, what do we want to do with this? We want to find the y coordinate of q. I must say, the first time I did this problem, I went on finding the x coordinate. It was really tedious, only to then have to find the y coordinate. So to find the y coordinate, we need to consider a simultaneous equation. We've got the equation of the hyperbola, which is that, and we're going to take the equation of the normal, make x the subject of it, because when we make x the subject, we're going to replace the x in the hyperbola equation, and then we're going to solve for y. Okay, so when we do that, we make x the subject of the top equation. We've got minus 2 root 2 all multiplied by y minus 4 equals x minus root 2 plus 1. We actually want to replace x plus 1, so that minus root 2 can go to the other side. Minus 2 root 2y plus 8 root 2 plus another root 2 is 9 root 2, and all of that equals to x plus 1. I'm going to factor out the root 2 before I continue. I've got root 2 times 9 minus 2y is equal to x plus 1. And then I go back to my hyperbola equation with x plus 1 and substitute this expression in. Root 2 times 9 minus 2y all squared minus y minus 2 all squared. I'm going to times everything through by 4. Put a 4 there and put a 4 there. Now, I could expand this all out. If I do, I will get a quadratic equation, but I know that one of the roots to this quadratic equation is y equals 4, because that's the y value of p. And I want the y value of q, the other solution to this quadratic. So what I can do is consider the product of the roots. When you have a quadratic equation like this, ay squared plus by plus c equals 0, the product of the roots is equal to the constant term c divided by the coefficient in front of the y squared term. So if I go to this quadratic and go, rather than expand it all out, what is the constant term? Where does that come from? It comes from this 9 bit here squared and the root 2 and the 4. And it comes from this minus 2 thing squared, and it comes from the 4 but on the other side of the equation. Okay, so the constant term for this quadratic equation is 9 squared, 81, times root 2 squared, so 81 times 2, times 4. 81 times 2 times 4. Then it's minus the negative 2 all squared from the second expression, so minus 4, and then it's minus another 4, the 4 moving to the left hand side. So that's the constant term. where does the a part come from? Well, that's the quadratic term. Quadratic term is this minus 2y expression squared, and then this term in here squared. Okay, so the first one, minus 2 all squared is 4, times root 2 squared is 4 times 2, and then times the 4 on the outside, and then minus the 1 from the second expression. Okay, and if we work out all of that, equals 640 over 31. And now that I've found the product of the roots, I go back to the fact that I only wanted the y value of q, and yq times yp is equal to 640 over 31. So yq must be the product of the roots 640 over 31, all divided by yp, which is 4. If you work that out, it comes out to be 160 over 31. Alrighty, part C of this problem could be solved using similar methods. So we've got the tangent at the point R is parallel to the tangent in P. Find the y-coordinate of the point S, where the normal at R meets the curve again in the region where x is greater than 0. So let's just look at our diagram over here. The tangent at the point R is parallel to the tangent at P. Now I never drew a tangent at P, and because I was only focusing on a normal, it's going to look something like that. And then there's another point on the curve where that tangent is parallel. It's going to be on the other side of the curve there, somewhere down here, R. And find the y-coordinate of the point S where the normal at R meets the curve again. So if I then go and take a normal at R, we've created a rectangle, and down here where this curve continues, it's going to be the coordinate S. Okay, so how do I find that coordinate? The diagram here is not to scale, so it's kind of hard to tell, but to find that coordinate S, we actually just need to use symmetry and the coordinate of Q. So I'm going to bring up GeoGebra so we can have a look at that, and just to confirm that the symmetry is going to help. Put the hyperbola in, put the point P in, it's called A but never mind, put a tangent in, it goes through that point and is tangent to the hyperbola. Now we need a parallel line that also touches the hyperbola on the other side. So if we consider the centre of the hyperbola, which is at 1, no it's not, it's at -1, 2, and you can see that the point A there is 2 above, and it's square root 2 to the right of that point. So if I go square root 2 to the left and 2 down, I'm at the coordinate which will be back on the hyperbola based on the symmetry of this. So another way of thinking about it is if I've got a circle centered at the center of the thing, and it goes through there, the other side of the circle, which is the coordinate -1 minus root 2, 0. That's the coordinate where the tangent will be parallel. Okay, so if I draw another tangent, or even a parallel line that goes through the point C, it turns out that that's a tangent. Now I want to put my normals in. And lastly, the intersection points. And you can see there, so it's a much better diagram, that the point D at the top left, if we can find that, and in fact we actually already have, because it's where the original normal in part B intersected point D is actually Q. If we know the Q value, then we can easily find the Y value of this new point S, which in this diagram is E. Using the symmetry, and I'll make it easier to see by just making a line between them. We need to compare the Y value of D with the centre, and then go in the opposite direction to find the Y value of E. If we were to do this using algebra and differentiation, we already know what the gradient is at the point P. We worked that out earlier. Therefore, that's the same as the gradient at the point R. So I would go down to this equation here for dy dx. The gradient at the point P is 2 root 2. I would go back and make the gradient function equal to 2 root 2 and solve for another value of theta. Find out that it's actually at 3 pi over 4. At that value of theta, we'd find the coordinates and find that the coordinates -1 minus root 2 comma 0, just like the GeoGebra diagram showed. Then I would find the normal at that point. Once I found the normal at that point, I would find out where it intersects the hyperbola again, so I'd be repeating the process that I just did. But the diagram on GeoGebra told us that some symmetry is going to help us. So to find the Y value here of S, I need to consider the centre and go how much higher than the centre is the point Q, and that distance in the Y direction I need to subtract off the Y value of the centre. Okay, so the Y value of S is equal to the Y value of the centre minus difference in Y values between Y and the centre and the Y value of Q. Okay, so the Y value of Q is equal to 160 over 31. Minus the Y value of the centre, which is 2. Okay, and if you work that out, it comes out to be 98 out of 31. And then I take the Y value of the point S is going to be equal to the centre, the Y value of the centre minus 98 over 31. And I work that out and it comes to be negative 36 over 31, which is the answer. You might want to confirm that by using the methods I talked about, finding the equation of the normal, simultaneous equation, and etc, etc. But it was a bit tedious the first time we did it, so I didn't really want to repeat that for this video. All the best for the exam.